Welcome back. In previous class, we have seen that the equivalent models of MOS transistor. Now, using those equivalent models, let us see the analysis of common source amplifier. The slide represents the circuit diagram of common source amplifier. It is similar to common emitter amplifier of BJT. Here, the MOSFET is for amplification. R1, R2 acts as a voltage divider circuit. Along with VDD, it acts as a biasing to provide operating point in the desired location. RD acts as a load resistance and also it is treated as the current limiting resistor, whereas CC1 is the coupling capacitor at the input, so that only AC signal is connected to amplifier, and if any DC component is present, that is not sent to the input of the amplifier. And Vs is the signal source at the input of this amplifier circuit. Now see the analysis, but before going to see the analysis, first of all you need to convert this amplifier circuit into small signal model. Okay, in the small signal model, what is the condition? All the VDD, the DC sources must be 0. DC sources 0 means it is in short circuit, therefore the VDD is connected to ground. Hence, when VDD is connected to ground, R1 comes in parallel with R2, whereas RD resistor comes between drain of the MOS transistor and ground. Okay. See the equivalent circuit. Now the MOSFET is replaced with the equivalent circuit, including the channel length modulation. Therefore, R0 comes in parallel with GM VGS. At the input, R1 parallel R2. After that, a voltage source as usual. At the output end, there is a drain resistor between drain to ground. Now, let us see the derivation of voltage gain first of all. For that, what is the output voltage in the upward diagram? The output voltage is the drop between the drop at the parallel connection of small RD and capital RD. That is minus GM VGS into small RD parallel capital RD. But where the VGS is from the input network, you can get it as by the voltage divider circuit. The VGS is derived as VI into RI divided by RI plus RSI. Where Ri is the input resistance, looking before the potential divider circuit. Okay. Now substituting this VGS in the V0 equation. The voltage gain AV is obtained as V0 by Vi equal to minus GM R0 parallel RD into Ri divided by Ri plus Rs. Okay. Like that you can derive the voltage gain in the common source amplifier. After that, let us see the input impedance derivation. For input impedance, that is before voltage divider network, if you see only one resistor you have, that is R1 parallel R2. And for output resistance, the condition is the Vs should be 0. Vs means Vi. Which means the VGS also 0. Therefore, at the output terminals, the resistance is R0 parallel small r, RD parallel, capital RD parallel small r0. That is the output resistance derivation for the CS amplifier. Okay. So in next class, you can see the analysis of of course the CS amplifier including the emitter resistor, but before going to see that one, let us solve one problem with reference to common source amplifier. As usual, find out the voltage gain, input and output resistances of common source amplifier with given data like VDD equal to 3.3 volts, The drain resistance RT is 10 kilo ohms, R1 is 140 kilo ohms, R2 is 60 kilo ohms, and RSI is 4 kilo ohms. The other parameters like threshold voltage is 0.4 volts, Kn is 0.5 milliamperes per volt, and lambda is 0.02. Okay, like that the data is given. From this you have to calculate VGS cube, IDQ you need to derive initially. So VGSQ is R2 divided by R1 plus R2 into VDD. So you can get the value as 0.99 volts. 99 volts. Okay, VGS. Then the drain current. Okay, is given as IDQ equal to Kn into VGS minus VT whole square. Okay, the coefficient drain current is given by the formula Kn of VGS cube minus VT. Because why this is the formula is used means because the transistor is operating the saturation for the amplification. Saturation region of MOS transistor for the amplification. Okay, its value comes 0.174 milliamperes. Now these two are ready. After that the VDSQ, that is the drain to source voltage with reference to operating point, that is VDD minus IDQ into RT. Okay, substituting all the values, hence you can get VDSQ is 1.56 volts. 1.56 volts. Now comparing the VDSQ and VGSQ minus VDN. By comparing these two, you can say that where is the transistor can operate? Is it in saturation region or non-saturation region? Okay. Now if you observe that VDSQ is greater than VGS minus VDN, therefore the transistor is biased in the saturation region. Okay. If this condition is not satisfied, the transistor operates in non-saturation region. But for amplification, it should be in the saturation region of MOS transistor characteristics, right? Then the small signal transconductance GM is, one of the formula for GM is 2 into square root of Kn IDQ. So if you substitute these values, Kn given, or otherwise Kn is Kn dash divided by 2 into W by L. At least that data may be given, so that its value comes like 0.590 milliamperes per volt. Now the small signal output resistance is, that is R0 equal to 1 by lambda IQ. This is small R0. Okay, small R0 value is 1 by lambda, that is channel length modulation value into IQ. So that its value is 287 kilo ohms. Then input impedance Ri is already derived formula R1 parallel R2, so which is 42 kilo ohms. And the small signal voltage gain, the voltage gain formula is AB equal to some minus GM R0 parallel capital RT, RL divided by RA plus RS. Therefore, substituting the values, you can get the gain as minus 5.21. Similarly, the output resistance is using the formula, that is RD parallel small R0, and the output resistance you can get as 9.66 kilo ohms. So like that you can solve the problems. You can practice more problems if you take the Niemann book. Okay. Now I am going to end this session. In the next class you can see the analysis of CS amplifier including the emitter resistor. Okay.